In the previous episode, I introduced to you what LLMs are and gave you a glimpse of their history since the 2000s. Today, it's time to explain the first thing that we need in our pipeline, the data. At its core, the idea behind a large language model is to simply predict the next word in a sentence. You heard me right. No magic generation of code, poetry, or conversations, just predicting the next word. We want to build a model such that, given an initial prompt, it can predict the next word and the next word and the next word until the sentence is finished. But why do we want that? Well, because we want our model to learn how sentences are structured and what words actually mean. Instead of trying to teach the model the rules of grammar, which is what researchers attempted to do back in the 80s,
a simple geographic question, depending on the phrasing, can lead to multiple interpretations. The program will determine the question's most likely meaning only after an exhaustive deconstruction of the sentence.
We're going to let the model figure out those rules on its own by feeding it tons and tons of text data. But LLMs can't just read raw text files the way we humans do. They only understand numbers. So because of that, we have to prepare our data first. Specifically, we need to use two techniques: tokenization and embedding. To see how this works, let's take a look at an example. Imagine we want to use a text to train our LLM. For example, Sabrina Carpenter's song Espresso. Since the model only understands numbers, our first instinct might be to just assign a unique ID number to every single word of the text. So the word now becomes 1, his becomes 2, thinking becomes 3, and every time she says that, it gets a 4. By the time we get to the end of the song, we've built a neat little lookup table of numbers, which we call our dictionary. That process is called tokenization. So now we have a sustainable way to turn Sabrina's lyrics into a sequence of token IDs. Problem solved, right? Well, not quite. We've stumbled into our next big challenge. Right now, these token IDs are just arbitrary numbers. If the token for latte is ID 105 and the token for espresso is ID 8432, the LLM has absolutely no idea that they are both caffeinated drinks. To the machine, 105 and 8432 are completely unrelated digits. That is, they don't carry any semantic context. So how do we give these numbers actual meaning? Instead of representing a word with just a single ID number, a more appropriate way is to transform that word into a vector. That is, an embedding vector. That allows us to represent words in a multidimensional space, where every dimension of the space represents a specific feature of language. In other words, the idea is that words with a similar meaning, like espresso and latte, will be closer together, whereas completely unrelated words like desperation and Nintendo will be far apart. In fact, back in 2013, Thomas Mikolov at Google introduced a breakthrough approach called word-to-vec, which became the golden standard for creating this static vector map all the way up until 2018. But mapping whole words this way presents a massive problem. What happens when Sabrina uses a contraction like thinking with an apostrophe and then later without one, or a brand new word the model has never seen before? The system would break because it doesn't have an ID for it. Also, the larger the dataset, the more IDs we'd have, making the dictionary huge and unsustainable. To fix that, we can chop our text into smaller pieces. There are three main ways of tokenizing. Word-based, which is what we've looked at so far. Every whole word gets an ID, and it's intuitive but highly inefficient and blows up the dictionary size. Character-based, where every individual letter gets its own ID. That way, our dictionary stays tiny, but the model loses all concept of word-level meaning. And finally, subword-based. This is the perfect middle ground. It keeps common whole words intact, but breaks rare words, typos, and contractions down into smaller chunks of letters. So instead of looking at whole words, a tokenizer breaks text down into smaller chunks called tokens. These can be whole words, but they can also be subwords, prefixes, or even individual characters. In fact, the most popular subword algorithm used by GPT and Llama is called Byte-Level Encoding, which we'll take a look at in a minute. Gemini, on the other hand, uses SentencePiece, which we'll also see. The tokenizer might take that contraction thinking and split it into two tokens, the root word think and the ending in. Because it can mix and match all these smaller pieces, an LLM only needs a fixed dictionary of about 32,000 to 100,000 tokens to build any word in existence. So in this initial lookup space we mentioned earlier, the model isn't actually mapping whole words like desperation or Nintendo. It's actually mapping subword fragments like des, er, at, ion, and nin. But these tokens are completely meaningless to you, you might say. So how does the model turn fragmented nonsense into a meaningful vector? This is where the embedding layer comes in, which is the very first part of an LLM. Inside this layer sits a giant spreadsheet called the embedding matrix. Every single row in this matrix represents a unique token from our vocabulary, and every column represents a dimension of the embedding space. Each of those values are called embedding weights. To give you an idea of the scale, the smallest GPT-2 models use an embedding size of 768 dimensions, meaning 768 columns, while the largest GPT-3 model uses an embedding size of 2,288 dimensions. But here's the trick. When we first start, this matrix is just filled with completely random numbers. The model has no idea what the subwords mean. Remember that our ultimate goal is to train this LLM to predict the next piece of text. At the beginning of the video, I called this predicting the next word, but now you know that under the hood, the model is actually predicting the next token. During training, we feed in a sentence, let it guess the next token, and measure how close it got to the actual text. So to reduce that error, the model uses a process that I will explain in the upcoming videos to adjust those random numbers in our matrix. By doing this over and over across millions of words, the values of every token shift until they represent actual contextual meaning. The first thing I'll do is to create requirements.txt with the three libraries we need for this episode. regex for Byte-Pair Encoding, SentencePiece for the comparison demo, and Torch for embeddings. Let's now set up the project structure. All the real logic lives inside an LLM package. The init.py files can stay empty for now. They just tell Python that LLM is a package we can import from. First, the text is split into chunks following a regular expression, which we'll see in a minute. For example, the independent department repeatedly managed the damage would be the following array. We'll keep the space at the beginning of the chunks to distinguish whether a sequence of letters appears at the start of a standalone word or within one. Then, each chunk is converted into its byte representation. For example, D becomes 84.104.101. Next, the most common adjacent pair of byte tokens across all chunks is found. For example, N 101.110 is one of the most common pairs, appearing twice in independent and once in department. That pair is then merged into a single new token everywhere, and this process is repeated until the target vocabulary size is reached or there are no more pairs left to merge. We'll start by importing the regex library to handle our text splitting. Next, we'll define a tokenization pattern. If we just blindly counted touching letters, the tokenizer would start merging characters across spaces and punctuation. It might merge the last letter of a word with a space next to it, or combine words with exclamation points. To prevent that, this regular expression uses the pipe symbol to split our text into 5 isolated categories before any merging begins. Let's break down those 5 parts. First, it handles contractions. The section starting with the apostrophe pulls out common English endings like apostrophe S, apostrophe T, apostrophe M, apostrophe LL, or apostrophe VE. This ensures a contraction like his always gets cleanly separated into he and apostrophe S. Second, it isolates letters. The PL stands for any letter in any language, and that little question mark handles an optional space in front of it. This groups whole chunks of alphabetic text together. Third, it isolates numbers.
The PN catches any numeric digits, ensuring numbers are kept completely separate from words. Fourth, it traps punctuation. This basically means match anything that is not a space, a letter, or a number. It explicitly groups symbols like exclamation points, commas, and question marks together so they don't corrupt our words. Finally, it handles white space. The last two sections catch sequential spaces and line breaks. Okay, so now we'll start creating the Python class that will represent our tokenizer. The initialization method will create three attributes for the class: merges to track the order of our byte pair combinations, vocab to map byte sequences to token IDs, and inverse vocab to quickly look up bytes from IDs during encoding. We pre-populate both dictionaries with the 256 byte values to ensure our model can process any input string without auto-vocabulary problems. Let's briefly talk about the three primary methods of our tokenizer. Train, which takes raw text and a target vocabulary size, and it performs the algorithm I described earlier to build our vocabulary. Encode, which transforms any input string into a sequence of integer token IDs using our vocabulary. And Decode, which reverses the process, converting a list of token IDs back into a readable text using our inverse vocabulary. To keep our three main methods elegant, we'll wrap up the class with a few helper functions. The first one is add to vocab, which takes a newly merged byte token, checks if it's already recorded, and assigns it to the next available sequence ID. The second helper function turns a raw text chunk into a list of single byte objects. The third helper method uses counter to scan through all our selected chunks, incrementing a frequency dictionary for every adjacent byte pair it observes. And finally, the helper function that merges, that is, loops through an isolated list of byte tokens, substituting any sequential occurrences of our target pair with a unified concatenated byte sequence. Now the train method takes a raw text string and our target vocabulary size. It uses our regular expression to pre-split the data into text chunks, converts those chunks into raw lists of bytes, and enters an iterative loop. In each iteration, it counts the most adjacent pair within chunk boundaries, executes a merge, logs the merge rule, and appends the next token to our vocabulary until our target size is reached. With a trained vocabulary, we can implement encode. This method transforms an input string into a list of integer token IDs. In particular, it splits the incoming text using our regular expression, converts each chunk to raw bytes, and runs through every merge rule in the exact sequence they were discovered during training. To reverse this process, we write the decode method. We just need to fetch the byte segments matching our list of integer IDs, stitching them together into a single continuous byte string, and decode it back to standard UTF-8 text. With errors equals replace, we can safely replace any corrupted characters. In this class, we'll also add a tokenized utility method which will spit out the merged byte objects. This can be useful for debugging or visualizing exactly where our tokenizer draws its subword boundaries on screen.
Finally, we can try our tokenizer by creating a file named train_bpe.py where we'll import the BPE tokenizer and train it on Sabrina's lyrics. I'll choose a vocabulary size of 512 tokens and I'll encode a random sentence from the song.
Let's set up a local virtual environment. That keeps this project's library separate from the rest of your system. To activate it on macOS or Linux, you can use the following command. On Windows, it's this one. I won't push .vmv to the repo since it's machine-specific and huge, so you can generate that locally. What we do push is requirements.txt, so you can run the following command. Now you can run your tokenizer. While Byte-Level Byte-Pair Encoding is a great starting point for understanding subword tokenization, other models like Google Gemini often rely on more advanced tokenization techniques like SentencePiece. SentencePiece is a lossless tokenization method, meaning that it reads text as a raw, continuous stream of characters, including white space. Because spaces are preserved as literal characters, decoding is entirely lossless. You simply stitch the tokens back together and swap the meta symbols back into normal spaces. This design makes SentencePiece completely language agnostic, allowing it to handle non-white space languages like Chinese the same way as in English. Furthermore, instead of relying on bottom-up merges like Byte-Pair Encoding, SentencePiece typically initializes a massive vocabulary of all possible character chunks and optimizes via a unigram language model. Specifically, it prunes away the least useful, lowest probability subwords over an iterative loop. When tokenizing a new sentence, it treats text segmentation as a mathematical optimization problem. It uses a graph-based dynamic programming algorithm, specifically the Viterbi algorithm, to calculate the absolute most probable and optimal way to break down a string based on the underlying probabilities of its subwords. Because calculating all these dynamic programming matrices are computationally heavy operations, SentencePiece is written in C++ to stay fast, and implementing this complete mathematical pipeline from scratch is quite complex. For this project, we'll simply import Google's optimized SentencePiece library. If you guys are interested in seeing how to implement that from scratch, let me know in the comments and I'll just create a dedicated video building it in C++. But for now, I feel like understanding the overall concept is more than enough. We won't be implementing the embedding layer from scratch because PyTorch allows us to instantiate and run these vectors directly on CUDA, that is the GPU. This is incredibly important because embedding weights are part of the overall model training, so keeping them on the GPU ensures that the training stays highly optimized and fast. While the weights are initially random,
PyTorch uses different pseudonumber generators,
depending on the hardware. For example, Mersenne Twister on the CPU and Phylox on the GPU. Both generators rely on operations such as bitwise shifts and XORs, but they differ in their design. Mersenne Twister is stateful and is typically generated sequentially, whereas Phylox is counter-based, allowing many random numbers to be generated independently and in parallel, making it well-suited for GPUs. The embedding layer acts as a lookup table that maps each discrete token ID to a continuous high-dimensional vector. You can check script/demo_embedding.py to print the vector shape and see the results in action.
So we programmed our tokenizers from scratch and initialized our first embedding matrix using PyTorch. Make sure you hit that subscribe button so you don't miss any step of this series. And if you run into bugs or have any question about the code we did today, feel free to use the comment section below to ask any questions. Thank you so much for watching, guys. I'll see you in the next one. Bye bye.